Okay, thanks very much for the invitation. So yesterday we talked a little bit about the history and background for the metric SYZ conjecture. We gave a survey about the progress on this whole program. And then we spent some time discussing the more basic aspects involving the complex geometry, the essential skeleton, and this dimensional reduction called the semi-flat metric. So that's where we were yesterday. So the goal of today is to kind of go through some of the somewhat more abstract aspect of the theory, notably explain the relationship between the non-Archimedean Monge-Ampère equation and this SYZ story. So we will discuss some kind of impressionistic aspect about what this non-Archimedean pluripotential theory is about. So we will mention an important property of this non-Archimedean Monge-Ampère solution called the weak comparison property, which is one of the key steps in proving the metric SYZ. And then in the extra time, we are going to mention something about the certain kind of offshoots of this work that applies in some more general context involving potential theoretic C0 limits. And we are also going to discuss an alternative viewpoint involving optimal transport. Okay, so let's begin by recalling what the metric SYZ is supposed to be about. So the goal is to find a special Lagrangian fibration for compact Calabi-Yaus with a polarization near the so-called large complex structure limit. So you want to find the special Lagrangian fibration, but there is a small measure subset that you would kind of lose all control about. So the kind of weaker goal, in some sense more reasonable goal, is to produce a special Lagrangian fibration away from a subset of small measure. Okay, so in other words, on the generic region. So that is our version of the metric SYZ conjecture. The ambitious audience members are welcome to think about global SYZ. So last time, what we said was that the C0 potential theoretic convergence is sufficient to imply the metric SYZ. So the key statement that you want to prove is that the Calabi-Yau metric on these degenerating complex manifolds have local potentials phi Calabi-Yau T, which are well approximated by a solution of the real Monge-Ampère equation. Determinant of Hessian is constant in suitable coordinates Zi after you impose suitable normalizations involving log T factors. So the key statement is about proving C0 potential theoretic convergence. And the reason for this is that if once you get C0, you can bootstrap to C infinity using Savin's result plus regularity theory of real Monge-Ampère. And once you go to C infinity, it's a matter of quite standard perturbation theory. So the key problem now becomes, can you understand the C0 potential theoretic limit of these Calabi-Yau potentials? So one intuition that is somewhat useful is that the Calabi-Yau potential should be approximately toric. So the toric nature comes from the dimensional reduction that we talked about last time. Namely, you have these local charts on C star to the n, and you would like the solution to be Tn invariant. Furthermore, the metric limit is supposed to be a real Monge-Ampère solution on the essential skeleton. So the Monge-Ampère equation comes from this dimensional reduction. The essential skeleton comes from this computation of the volume that we went through last time, which explained where the volume of this Calabi-Yau measure is kind of concentrated. And that turns out to be encoded combinatorially by the kind of top dimensional faces of the essential skeleton. So from a sort of naive perspective, or in some sense, the most straightforward thing that one would like to do is to first find a solution to the Riemann-Champay equation on the essential skeleton. So this is about, okay, so the SYZ general heuristic kind of tells us that we should have some solution to the Riemann-Champay equation as the suitable potential theoretic limit to these Calabi-Yau potentials. But so then the natural strategy would be you first try to produce a solution to this Riemann-Champay equation, and then you try to somehow show that this solution is unique and is the limit of these Calabi-Yau potentials. So that is, in some sense, the natural strategy. So you need to produce a solution and you need to show convergence. Okay, so after some thought, you realize this is actually quite a difficult problem. And difficult not just in the sense that it's difficult to solve, but even in the sense that it's difficult to formulate precisely. Okay, why is it? So you want to solve the Riemann-Champay equation, that is determinant of Hessian is equal to constant, on this essential skeleton. Okay, but what kind of object is the essential skeleton? So a priori, it is given to you as a simplicial complex. And furthermore, the simplicial complex structure, in fact, also depends on the choice of the model. So if you choose a different model, it would be the same simplicial complex, but kind of subject to further subdivision. So basically, the simplicial structure depends on the model, while as an underlying set, this simplicial complex doesn't change. But the point is that the essential skeleton has no natural canonical affine structure a priori given to you. Now, if you want to formulate the Riemann-Champay equation, determinant of Hessian is equal to constant. In the classical story, you need to basically do two things. One is you need to know which U is convex. So the classical theory of Riemann-Champay equation, you first define what convex function means, and then you make sense of this equation in a weak way. There are several ways to make sense of this. For instance, you can use Alexandrov weak solution. But basically, you need two things. One is you need to know which class of function is convex. The other is that you need some weak formulation of the Riemann-Champay equation. Okay, but this is not a priori clear on the essential skeleton, because if you want to formulate when a function is convex, then you need the transition functions between the different charts to be affine linear. Okay, so on the essential skeleton, however, the essential skeleton is just a simplicial complex. So if you kind of take different charts and compute their transition functions, they are not affine linear, but only piecewise affine linear. So if your transition function is piecewise affine linear, then a convex function in one chart may not be a convex function in a different chart. So even the class of function is not a priori easy to define. Now, if you want to formulate a global Riemann-Champay equation, you also need the transition to be affine linear. So if you just have a piecewise linear affine transition function, and then you define the Riemann-Champay equation in one chart, and compare it to a different chart, you would pick up some kind of delta distributions along the piecewise kind of non-smooth locus of the transition function. So both problems involve somehow knowing a good choice of affine structure, which is not a priori so clear from the problem. By the way, so I think Jakob has some other ideas about possibly picking out a kind of distinguished sort of affine structure or something. So we can listen more to his talk for his suggestion on this problem. But at least a priori speaking, there is no distinguished affine structure, and that makes even the formulation of the problem hard. And even if you can somehow solve this Riemann-Champel equation, there is still this rather serious question of how you can compare this to the Calabi-Yau potential, because the Riemann-Champel equation lives on the essential skeleton, while the Calabi-Yau potentials live on the Calabi-Yau manifolds, which are complex manifolds. So these are objects of quite different flavors, and even their dimensions are quite different. Now, the solution of this problem, which is quite a big jump, is to use non-Archimedean pluripotential theory. So instead of working on the essential skeleton, you work on something called the Berkovich space. Okay, so this is maybe a little bit of a too big of a conceptual jump, so I can only give you some impressionistic feeling about what these things are. So the points on the Berkovich space can be viewed as valuations, and the essential skeleton can be embedded into the Berkovich space, which means in particular that the points on the essential skeleton have an interpretation as valuations. In fact, every dual complex for every choice of the model of the degeneration gives rise to a subset of the Berkovich space. So as you take larger and larger blow-ups, the dual complexes become bigger and bigger, and the Berkovich space should be viewed as a gigantic object that contains all the dual complexes as part of its subset. So this is a very big object. So there are two ways to compare this to dual complexes. There's an embedding map, and there's also a retraction map. Furthermore, there is a hybrid topology which unifies the complex manifolds XT with the Berkovich space. So one way to view this is that the Berkovich space can be viewed as the tropical limit of these complex manifolds. And if you really hate this Berkovich space, then I encourage you to think of a dual complex as the replacement of the Berkovich space. And furthermore, there is a Lebesgue measure on the essential skeleton. So the essential skeleton is a simplicial complex with a natural integral structure, so that gives rise to a Lebesgue measure. And it can be viewed as the hybrid topological limit of the normalized Calabi-Yau measures on XT. So normalized means you normalize the total measure to 1.
Oh, fine.
All right. So there is furthermore a notion of semi-positive potential on the Berkovich space, from which you can develop a theory of Monod-Champel equation, which is defined in terms of intersection theory and F-line bundles, etc. The details of which is not going to be hugely important to us. So the central result of that theory is the solution of a non-Archimedean version of the Calabi conjecture, which says there is a unique up to constant PSH potential on the line bundle over the Berkovich space that solves this non-Archimedean Monod-Champel equation. So that is to say, the non-Archimedean Monod-Champel measure is equal to this Lebesgue measure mu0 up to this factor of Ln, that is the intersection number of this line bundle. So we call this U the non-Archimedean Calabi-Yau potential. Okay, so this is a very brief overview about what the non-Archimedean pluripotential theory is about. So you have this space built from valuations that somehow includes all these dual complexes as subsets, and somehow you have a pluripotential theory on this gadget. And the key property is that you have this Archimedean Calabi-Yau potential. Okay, so the explanation about the Berkovich space. So the intuition is that the Berkovich space is the tropical limit of xt as t goes to 0. Okay, so what are the points on this space? So these points can be viewed as the semi-valuations on the ring of functions. So just to give you some examples about certain points on the Berkovich space, for instance, suppose you are given an SNC model. So over the disk, so you can try to base change to C double bracket of T. This is the formal disk. The central fiber is, as yesterday, just sum of BI EI with the components EI. So this gives rise to the divisorial valuations. So for each divisor component EI and any local holomorphic function in the ring of functions, you can evaluate the order of vanishing along the EI. So this gives you a certain valuation. And you have this normalization factor BI, which kind of encodes the multiplicity of this divisor component. So once you kind of suitably normalize, you get a so-called divisorial valuation. So this sets up a correspondence between the divisor components on the central fiber and certain valuations. So this is an explanation that the vertices of the dual complex, which correspond to these divisor components, can in fact intrinsically be viewed as divisorial valuations, and therefore these are points on the Berkovich space. So somewhat more generally, any point on the dual complex for a given model can be understood as monomial valuations that I'm not going to explain too much further. But the point is that every point on the dual complex can be viewed as valuation, and therefore can be viewed as a point on this rather abstract thing called the Berkovich space. In other words, the dual complex embeds into the Berkovich space. So this gives you some sense about what kind of points are there on the Berkovich space. So I mentioned there's a retraction map. So instead of telling you exactly what it is, it's probably better to give you some intuition about it. So you should view the retraction map as the non-Archimedean analog of the logarithm map. So remember that in our computation of this volume form, integral of omega wedge omega bar, we somehow needed to take local coordinates z1 onto zm with z1 kind of product onto zm is equal to t. So these are part of the coordinate system around these intersection strata. And this tells you that if you take these logarithms after normalizing by these log t factors, you will end up in the simplex that xi are bigger or equal to 0, and sum of xi is equal to 1. So in other words, you have some local charts with target in certain simplices that appear in the dual complex. So these are the logarithm maps, and you should think of the retraction maps on the Berkovich space as the non-Archimedean version of this thing. So how does the hybrid topology work? So hybrid topology is something that unifies the complex manifolds with the non-Archimedean topology. So it kind of so it's trying to take two very different types of objects, the complex manifolds and simplicial complexes, and somehow put a topology on both of them. So how does this roughly work? Okay, so the convergence of a sequence of points on xt to a point on the Berkovich space, roughly speaking, looks like the following. So you have some model for the degeneration, SNC model, and you have some intersection strata EJ, the intersection of some EI, and the local coordinates are ZI. So when a sequence of points on the complex manifolds are converging to a point on the m-dimensional simplex inside the dual complex, which is a subset of the Berkovich space, then complex geometrically, these points ZT will converge to the intersection strata EJ in the central fiber, and these normalized coordinates will converge to the coordinates on the simplex. Okay, so this is roughly speaking how the hybrid topology works. So you should imagine locally you have these kind of C star to the M charts, and somehow up to these logarithmic normalizations, you just have the convergence of logarithmic coordinates to the coordinates on the simplices. So that is roughly speaking how this hybrid topology works. So if you want a slogan, hybrid topology encodes logarithm. So somehow there's an intrinsic amount of transcendental phenomena going on involving exponentials and logarithms, and non-Archimedean geometry is the right language to encode this transcendental aspect. So remember that the metric limit is not going to be an algebraic variety. Instead, it has to be a transcendental object. And this transcendental phenomena is reflected in this exponential and logarithms. Okay, so having explained to you what Berkovich space roughly is and what a hybrid topology roughly works, let me tell you something about the PSH potentials. So one way to think about PSH potentials in Kähler geometry is that once you have a projective manifold, then the Kähler matrix in the first-gen class of a line bundle can be viewed as limits of Fubini-Studi matrix. So this is a quite standard fact in Kähler geometry. So similarly, in non-Archimedean pluripotential theory, there is also a notion of Fubini-Studi potential, and the more general continuous PSH potentials are just the C0 limits of these Fubini-Studi potentials. In other words, the Fubini-Studi approximation is an equivalent definition of what it means to be a continuous PSH potential in non-Archimedean geometry. So there are a number of equivalent definitions, and this is one of them. Okay, so now let me talk about the main condition that you would like to hold on the solution of this complex Monchampel equation, on this non-Archimedean Monchampel equation. So this is what I call the weak comparison principle, or weak comparison property. So what it says is the following. So you want there to be some SNC model for the polarized degeneration family. And you want to find an open subset of 4 Lebesgue measure, such that under the retraction map from the Berkovich space to the dual complex, the non-Archimedean Calabi-Yau potential U satisfies that U is invariant under the retraction map on the subset which is defined by the preimage of U under this retraction map. Okay, so this might look somewhat abstract. So a kind of heuristic way to think about this is as follows. So you should think of these retraction maps as non-Chemidian analog of log. So this claim that U is invariant under the retraction map means that there is a function U that lives not just on the Bekovich space, which is a gigantic, huge, monstrous object, but rather on something much smaller, the dual complex, or if you like, some open part of the essential skeleton, such that the potential here is constant along the fibers. So what this means is that the analog of this is that the Calabi-Yau potential should be similar to U of U composed with this log map. So remember that the semi-flat metric is just a dimensional reduction that phi is U composed with logarithm with this log t scaling, where U satisfies that determinant of Hessian is equal to constant. So the weak comparison principle property can be viewed as just the non-Chemidian analog of saying that the potential is pulled back by this logarithm map. So the correct analog should be that it is the pullback of this retraction map. Okay, so this is the weak comparison property. The intuition is that the non-Chemidian Calabi-Yau potential looks toric, which would be a suggestion once you believe that the non-Chemidian Calabi-Yau potential is basically the limiting thing for the Calabi-Yau potential on the complex manifold, then the non-Chemidian guy being toric would strongly suggest that the Calabi-Yau potentials on the complex manifolds are also close to being toric. The second remark is that the weak comparison property is independent of the choice of SNC models. And that's basically because if you blow up SNC models further, then you might change the simplicial structure, etc., on the essential skeleton, but it would not affect things on open dense four-measure subsets. So why is it called comparison property? Because if this property holds, then it was known by a result of Christian-Welsmeyer that you can compare the non-Chemidian Monchampay measure with the real Monchampay equation. So that we will discuss a bit later. So if this weak comparison property holds, the result of Christian-Welsmeyer says the following. It says if this weak comparison holds, then the non-Chemidian Calabi-Yau potential satisfies the real Monchampay equation. Okay, so the weak comparison property basically says that non-Chemidian Calabi-Yau potential boils down to this function U that lives on the open parts of the essential skeleton. And the result of Christian-Welsmeyer says that it satisfies the equation. Okay, so basically non-Archimedean geometry kind of resolves the early problems that we mentioned. So one problem was it's hard to define what it means to be a convex function on the essential skeleton. The other problem was it's hard to formulate what it means to solve the Riemann-Champy equation on the essential skeleton. So as you see, once the weak comparison property holds, it would simultaneously solve both problems. The solution of the first problem, which is what does it mean to be a convex function on the essential skeleton, the solution is that you should just take the PSH potentials on the Berkovich space and restrict them to the essential skeleton of X. Okay, the second question was how do you want to formulate the Riemann-Champy equation on the essential skeleton? The answer is you don't try to do it directly. You just look for a solution of this non-Archimedean-Champy equation, and if you can prove the weak comparison property, that automatically give you a solution of the Riemann-Champy equation. Okay, so that was the background on non-Archimedean fluid potential theory. Now let's talk about one of the central connections to SYZ conjecture. So this was understood a few years ago that the weak comparison property would imply the metric SYZ conjecture. So let's recall the main problem. So as we explained last time, you can reduce the proof of the metric SYZ conjecture to proving this C0 convergence statement. That is to say, you want on the generic region, that is to say a subset of very large measure, you want to find the local Calabi-Yau potentials and show that they are C0 converging to the solution of a Riemann-Champy equation. So that was the main problem that you want to address. What this non-Archimedean fluid potential theory produces to you is the solution of the non-Archimedean Calabi-Yau potential. So then the basic strategy in proving the metric SYZ is basically you start with this non-Archimedean Calabi-Yau potential, and you try to somehow compare this with the Calabi-Yau potential on the complex manifold fibers XT. So basically what happens with non-Archimedean Calabi-Yau potential is that it produces the candidate function U, which solves this Riemann-Champy equation. So the problem left would be you want to compare this U with this Calabi-Yau potential on the complex manifold. So this would require some input from complex fluid potential theory, and the central task is you want to be able to compare two different potentials. So by compare, I mean you want to estimate the difference between these two things. Okay, so let's now discuss some kind of background techniques in complex fluid potential theory. So if you're on a fixed scalar manifold, that is the more standard setting of the theory developed by people like Calabi-Yau. Suppose you have two potentials, phi and psi, with bounds on the complex Mon-Champy measure density. Then there are basically two main conclusions. One is if you know that these two potentials are close to each other in some rather weak norm, such as L1, then under some density bounds, you can conclude that their difference is in fact small in L infinity. So this is sometimes known as a stability estimate. The other result, which of a similar flavor, is that if you know these two volume densities are close in L1, then you can also conclude that the two potentials differ by a very small amount in L infinity. So in other words, if either your two potentials are kind of close together in some rather weak norm, or if their kind of complex Monchampay measures are close to each other in some rather weak norm, then you can conclude that these two potentials are very, very close in C0. So this was quite standard on a fixed scalar manifold. And the point is that there are in fact uniform versions of these things, even when the complex structure starts to degenerate. So maybe as a somewhat technical remark, you really need these two potentials to be globally defined. Even if you just want to compare two potentials in the generic region, in order to apply the Calabi package, you have to ensure that these potentials are globally PSH on the entire manifold. So you can't just define these things on a large measure subset. That is not enough. Okay, so how does the approach via non-Archimedean geometry roughly look like? Okay, so this is a kind of strategy sketch. So you use this non-Archimedean geometry to produce the non-Archimedean Calabi-Yau potential U. Okay, so let's assume this weak comparison property. So you can that allows you to regard U not just as something that lives on this rather abstract thing called the Berkovich space, but on something much more concrete, which is like a dual complex. So by the result of Wels-Meyer, this U would solve the real Monchampay equation. So that gives you the candidate limit on the essential skeleton. Now, as I said, you need to ensure global PSH property, and this is done by Fubini-Studi approximation. So the end result of that thing would be you produce a global Kähler potential on the complex fibers, which is C0 close to U on the generic region of XT. So how do you ensure that the sort of PSH property is preserved? Well, so by the definition of PSH property in the non-Archimedean world, you can find non-Archimedean Fubini-Studi potentials to approximate your U, which is the non-Archimedean Calabi-Yau potential. Now, the point is that non-Archimedean Fubini potentials can be viewed as C0 limits of Fubini-Studi potentials on the complex manifolds. So basically, going through the Fubini-Studi approximation, you can ensure that everything in the construction is PSH. So after some further regularization procedure, you can ensure that the volume density of this auxiliary potential you constructed is close to being Calabi-Yau in some rather weak sense. Okay, so this, morally speaking, comes from the fact that U solves the real Monchampay equation. Therefore, something close to U has complex Monchampay roughly equal to the one you want. So once you have these properties, then you can deduce the C0 convergence of the Calabi-Yau potentials to U. Morally speaking, by utilizing this Calabi package in a rather degenerate setting. So the subtlety here is that these complex structures are highly degenerate. Okay, so the way you deal with the degeneration of complex structure is that you try to check that in Calabi-Yau's estimates, the actual dependence on complex structure, it uses very minimal information about the complex structure. You just need to prove a uniform version of the so-called Skoda estimate. The second technical issue is that, so here I needed to compare the actual Calabi-Yau potential with this auxiliary thing that I called psi. And in the usual cohomology package, you would need the volume densities of both potentials to be somehow controlled a priori. So this is not quite true for psi in our setting. So what you need to do instead is you need to apply an asymmetric version of Calabi-Yau's argument, so that you only get an inequality in one direction rather than in both directions. And for the other direction, you need to use some additional arguments involving mean value inequalities and other things. Anyway, so the upshot of this slightly technical digression in complex pluripotential theory is that once you have the weak comparison property on this non-Archimedean Calabi-Yau potential, that implies the metric SYZ conjecture. So the rough logic being once, so the Sebastian Buchsbaum, Johnson and Favre result tells you there is this non-Archimedean pluripotential theoretic solution to the non-Archimedean-Monchampel equation. If you know the weak comparison property, you know this is also a solution of real Monchampel. And then by this pluripotential theory arguments, you can show this thing is close to your true Calabi-Yau potential. And once you have that, you verify the kind of key claim here that the Calabi-Yau potential is close to this real Monchampel equation solution. Okay, so that is the rough logic of why weak comparison property implies metric SYZ. Okay, so in the remaining time, we will discuss some other developments kind of involving similar techniques and some other viewpoints. So a few years later, I also proved this following result. So for all polarized degenerations of compact Calabi-Yau manifolds with essential skeleton dimension between 1 and n, then up to an additional, up to an additive normalization constant, the Calabi-Yau potentials on these complex manifolds converge in the C0 hybrid topology sense to the non-Archimedean Calabi-Yau potential U on the Berkovich space. So notice that the large complex structure limit is the special case where the dimension of the essential skeleton is equal to n. So this kind of includes all the cases between 1 and n. So the case where the dimension of essential skeleton is equal to 0 is, well, in some sense, not the interesting case, because then the essential skeleton is just a point, and then the statement is kind of vacuous. So some of the cases covered by this more general result includes these following examples. So you can have a Fano manifold M, and then you can take these hypersurfaces given by this equation that the product of Fi plus Tf is equal to 0, where the Fi's are sections of certain powers of the line bundle, so that the total degree add up to the anti-canonical of the Fano manifold. The other comment is that this theorem does not assume the weak comparison property. So to prove that the weak comparison property implies metric SYZ, what you need to know is just the C0 convergence of the potential on the generic region only. Okay, so the above theorem has one aspect which is stronger than this, in the sense that it deals with global C0 convergence. That is to say, not just in the generic region. So this tells you also something about the potentials in the non-generic region as well. And for that, you need a rather tricky argument involving Osawa-Takikoshi extension theorem. Okay, so this is some discussion about further developments in the direction of how the non-Archimedean Calabi-Yau potential is related to the true Calabi-Yau potential, going beyond the case of large complex structure limit. So there's a further direction that I would like to discuss, which involves optimal transport. So the more differential geometrically inclined audience members would have already probably hated this non-Archimedean thing, because it sounds quite general, but sounds really abstract. So there's an alternative idea that I learned from the works of Jakob and his collaborators that involves optimal transport problem instead of non-Archimedean. So the optimal transport problem suggested by these authors are specifically designed for toric funnel hypersurface examples. So in some sense, not the most general thing. So the non-Archimedean approach has the advantage of being general. The optimal transport approach has the advantage of being concrete. So let's talk about some special cases. So you start with a toric funnel manifold, which is encoded combinatorially by a integral reflexive polytope of dimension n+1. And the dual polytope is denoted as delta check. So this X delta is the toric funnel manifold with this prescribed delta polytope. This X canonical is the distinguished anti-canonical section corresponding to the toric boundary divisor. And so if you take it from the viewpoint of the reflexive polytope, this is the section corresponding to the origin. That is the unique interior point of this polytope. So F is chosen to be suitably generic. So in this case, the essential skeleton can be just identified as the boundary of this delta check. And then, okay, so you need to answer the question about what class of convex functions you want to consider. And there is a natural class of Kähler potentials that are natural to these hypersurface examples. So so the question you want to answer is, how can I produce Kähler potentials on these hypersurfaces? And there's a natural answer, which is if you can start with a Kähler potential on the ambient toric funnel manifold, then just by restricting these potentials, you would get potentials on hypersurfaces. Okay, so it's a natural and simple idea. Now, if you are on a toric manifold, then the torus symmetric potentials are very easy to understand. So they just correspond to convex functions on Rn with specific asymptote near infinity. Okay, so that was the motivation of these Lagrange transform things. So the Lagrange transform is quite simple. So you start with C0 functions on the boundary of either this polytope delta or its dual delta check, and you just do this Lagrange transform. So the point of this Lagrange transform is that the class of functions that you get from these Lagrange transforms essentially is just the same thing as the toric Kähler potentials on the ambient toric Fano manifold in the correct Kähler class. So that was the motivation of why you want to consider these Lagrange transforms. So this gives you a distinguished subclass of convex functions on the boundary of the polytope. And from this data, you can write down something called the Kontorovich functional. So we saw something along these lines in yesterday's talk by McCann. So the Kontorovich functional involves the integral of phi with respect to the measure on the domain, and the integral of its Lagrange transform with respect to a measure on the target. So here the domain and target are just the boundary of the polytope and the boundary of the dual polytope. So as you can see, it's a fairly symmetric setting. And there is a unique minimizer in this class of functions up to an additive constant. So this you can prove fairly easily. So furthermore, if you analyze this variational problem, you can show that the additional combinatorial condition, so under an additional combinatorial condition about these polytopes, so roughly speaking, what the condition says is that if you take integer points on these integral polytopes, there's a natural pairing between delta and delta check, and you require that these pairings never take the value 0. So it's a very explicit condition on delta. So under this slightly ad hoc condition, you can show that this unique minimizer of the Kontorovich functional agrees with the restriction of this non-Archimedean Calabi-Yau potential to the essential skeleton. And you can further prove the weak comparison property, hence deduce the metric SYZ. So morally speaking, the rough logic is that once you have this minimizer, and you know that the, let's say the, okay, so once you have this minimizer, you can talk about the conjugate points on delta and delta check on these two, the boundary of the two polytopes. So if you can prove certain property about the gradient of this map, then somehow you can show that this minimizer agrees with a solution of the Riemann-Champel equation. And once you have that, you can basically check that this thing agrees with non-Archimedean Calabi-Yau potential. So somehow the rough idea is that if you are somehow able to produce a Riemann-Champel solution by whatever means, then by some uniqueness result of this non-Archimedean Calabi-Yau potential, all of these solutions have to be the same thing. So that is the rough intuition behind this. Moreover, in this case, you can also directly prove metric SYZ without appealing to non-Archimedean geometry. So that was, I think, an observation of Jakob and his student Andreasen. So in some sense, non-Archimedean geometry in very concrete examples, like these toric funnel hypersurfaces, is not strictly indispensable. So if you have a concrete setting, you can just use your Kantorovich functional to formulate a variational problem, which you can also view as an optimal transport problem. And by solving this variational problem, you can directly prove metric SYZ without going through this non-Archimedean nonsense. So that was, in my view, a quite nice viewpoint on this story. There are some further results of Jakob and Andreasen about when exactly do these conditions hold. So they have some numerical results showing that the combinatorial condition holds for a few hundred examples in dimension 3. But for many other examples, they also show that the optimal transport problem is ill-behaved in the sense that it cannot possibly agree with either the limit of Calabi-Yau potentials or this non-Archimedean Calabi-Yau potential. So this is, by computing, somehow the certain measures on certain subfaces of both the domain and target, and show that somehow the optimal transport cannot map a large amount of measure into a small region. So some logic of this kind shows that the optimal transport somehow works in certain cases, but not in the other cases. Okay, so that was quite a puzzle at that time. So the sort of insight in hindsight is the following, that, okay, so this particular Kantorovich functional that we wrote down, involving a class of functions phi and their Legendre transforms, should be viewed as only a first approximation to the true optimal transport problem for this on this essential skeleton. So somehow the problem is that you are not really using the correct class of convex functions. You are just using the subset of convex potentials that somehow extend to the toric PSH potentials on the ambient funnel manifold. And that is only a subset of the correct class of convex potentials. And so the rough reason why this works sometimes but not in the others is that you are using a smaller class of convex potentials than the correct class. So when the minimizer of when the correct non-Archimedean Calabi-Yau potential happens to lie in this more restricted class, then this method has a chance. Otherwise, this method would have to fail. So that was, in some sense, the reason why this optimal transport approach kind of works sometimes, but not in all the possible cases. Okay, so just to give you a recap about what we discussed so far. So we talked about some motivations of non-Archimedean, what this non-Archimedean thing roughly is about. We had a crash discussion on Berkovich space. We talked about this weak comparison property, and this was, in some sense, the key thing for the metric SYZ. So for the past several years, that was the main missing thing that we don't understand. So we discussed a little bit about the complex pluripotential theoretic approach of Kologi and others. So involving comparing two Kähler potentials. So that kind of somehow shows that once you have this weak comparison property for your non-Archimedean Calabi-Yau potential, then you can deduce this thing is close to your true Calabi-Yau potential, and then using what we said yesterday, that's enough to imply metric SYZ. And finally, we had some discussion about a more explicit, concrete approach involving optimal transport, which has the advantage of being quite concrete, but has the disadvantage of not working always. Okay, so in the next lecture, we are going to talk more about how to finally get to the weak comparison property. So that was the main missing ingredient in the last few years. And in next talk, we are also going to discuss more about a refinement of this optimal transport problem. So it turns out that what happens with the previous approach was that the class of convex functions was not exactly the correct one. And you need to extract a much more mysterious cost function and use that to define a better version of the optimal transport that turns out to be equivalent to the non-Euclidean Monge-Ampère equation. Okay, so that's what I want to discuss today.